when we were first introduced to the imaginary unit called I, you might remember that I was maybe a little extra careful not to say that we define I as the square root of -1. That's because square roots are problematic for reasons that I want to kind of use this video to help us expose and to get us to think not just about how we should be considering complex functions in different ways, but also how this entire problematic industry of finding the inverse of an invertible function shows up across the curriculum in the high school frameworks. So what's the problem with square roots? Why do I say that they're problematic, and how does this give us an entry point into thinking more deeply about complex functions? So I have two conundrums for you in this video. The first one is a teaching-related conundrum, and it's one that if you teach high school algebra, you probably run across this repeatedly in the course of an average year. And the conundrum goes like this. Students are told in their pre-algebra curriculum what the square root of 16 is, for example, right? And usually the way that we introduce this is we tell students it's a number that solves x squared equals 16. It's something which, when you multiply it by itself, gives you the number that's underneath the radical. So square root of 16 is written as 4. Great. This is a great way to introduce the concept of a square root to students who are not familiar with it. Then the student gets to algebra, and they're given an equation like x squared equals 16 and told to solve this equation. So the student says, oh, I remember this. This is exactly the equation which is definitionally the square root of 16. And so x must be the square root of 16, which is 4. And then that answer gets marked as incorrect. Are we talking out of both sides of our mouth here as math teachers, right? What is the resolution to this seeming tension? Well, viewer, as somebody that's familiar with the high school math curriculum, I'm sure that you see the difference between these two things, right? That defining what square root means and solving a quadratic equation are not coextensive processes, right? That if I'm solving x squared equals 16, what I want the student to come up with all solutions to that equation. But the square root, per se, is only ever going to give us one output. Why? Because we insist that square root, like everything else that we do in the middle and high school curriculum, and we can thank our buddy Felix Klein for this in a lot of ways, we insist that the processes that we study be functions. We insist that they only have a single output value. So if I put 16 into the square root, I expect to get out a single number, namely the number 4 is what I expect. And if I ask a calculator, that's what the calculator is going to tell me, right? But when I'm solving a quadratic equation, we want students to be sensitive to the fact that equations can have more than one solution in general. So we want the student there to come up with 4, but also come up with -4. And so the student at that point would rightly say, well, what did I miss? Like, how should I know that I need 2 solutions to this? How come the square root doesn't spit out both of those solutions? Or how am I going to remember that if I get a positive solution for an equation that I also need its opposite to also be a solution? Is that always the case, et cetera, right? So what's going on here? Well, what's going on and why quadratic equations are usually students' first exposure to equations that have multiple solutions is that unlike linear functions, quadratic functions in general are not one-to-one functions. That if I put 2 different inputs into a quadratic function, it's possible for that function to turn those 2 different inputs to the same output, which is not something that linear functions can do, for example, which is why quadratics are the first place students tend to encounter this idea. So what might be a better way? So how can we help students to resolve this tension when it comes up? And I promise it comes up every year in Algebra 1 and Algebra 2 contexts, right? Well, if we ran the world together, maybe someday we will, we could rewind the tape to pre-algebra and insist on being extra careful with language when we introduce students to the concept of square root. Some teachers are very careful about this. Some textbooks are very careful about it. Some textbooks are not very careful about this, which means some teachers are also sometimes not careful about this. So if we just say a number that solves x squared equals 16 is what we mean by the square root of 16, there are two possibilities for what that number could be, a positive version and a negative version. Right? Whereas if I write radical 16, I mean a single object. So probably the best resolution would be to change the language with which we introduce the square root in the first place by adding a clarifying word, the word positive. I suppose we should have said non-negative. Maybe I'll change that right now on the fly. The square root of 16 is a non-negative number, which solves the equation x squared equals 16. So the square root of 16 is going to be positive 4 because we've added this clause in there, non-negative. And adding that clause, it turns out, is enough to differentiate the output that we want from the other output which otherwise would have solved that equation. So just by insisting on the non-negativity of the output of the square root is enough to tell the two different solutions of x squared equals 16 apart and kind of privilege one of those solutions over the other. We like square root to output a positive answer. Why? History. Somehow, cognitively speaking, we learn what positive numbers are before we learn what negative numbers are, and so positive numbers tend to be cognitively preferred by most people over negative numbers when the choice is arbitrary. But one of the points that I want to drive home in what we talk about this week is that those kinds of choices can be motivated by things we sort of like, right? Preferences that we have, cognitive cheats and cognitive biases. But fundamentally, those choices are often arbitrary. We could just as well have resided in an alternative universe in which the square root that we write down in the pre-algebra classroom spits out a non-positive answer instead of a non-negative answer, where the square root of 16 could be considered to be negative 4 instead of positive 4. But somewhere along the line, we made the choice that square root is going to spit out non-negative results. That choice is really a choice about how to render the squaring function invertible. So as we're going to talk about, invertible functions necessarily need to be one-to-one. It's not possible to take two different inputs and produce a common output for those two inputs and then be able to go backwards in a unique way, which is what we insist if we want the inverse to be a function and not a multi-valued relation. So here's another really surprising place where this can show up. And this, we're going to bring in our complex number knowledge here as well. And I love showing this example to students soon after they learn about what I is and where it comes from. Here's a mathematical conundrum that involves the square root again, and which I hope further highlights how square roots can be problematic. So I'm going to try to convince you that 1 is equal to negative 1. So 1 is equal to the square root of 1, which is the square root of negative 1 times negative 1. I can split apart the square root over a product, and then each of those square roots is I. But I times I is negative 1. That went by pretty fast, so let's take a look at it again. How can I take the square root of 1? Well, I can replace 1 by negative 1 times negative 1. Then I can distribute the square root across the product, evaluate each of those square roots to be I, but then I times I is negative 1. What in the world is going on there? Right. How could each of these steps be true if they lead us to the conclusion that 1 must be equal to negative 1? And of course the answer is that at least one of the steps that we applied in the simplification of this equation must be invalid in this case. And yet each one of those steps doesn't seem controversial. 1 is equal to negative 1 times negative 1. The square root of a product is the product of the square roots. And the square root of negative 1 really is I. And I times I really is negative 1. So what in the world is going on there? What I'm hoping our discussion this week will allow us to do, and we're going to take kind of a long and winding road to get there, unfortunately, we're ultimately driving to compare and contrast complex analogs of familiar functions from the secondary curriculum with their real variable counterparts. So we've spent a few minutes already kind of talking about the square root as a function and what might be different in the realm of square roots when we are now thinking of a complex square root function rather than a real valued square root function. And as you might suspect, that discussion is going to center, it's going to revolve around this idea that picking an inverse for a non-one-to-one function involves explicit choices. And those are choices that we are empowered to make, but that we should be aware that we're making them so that we can qualify and appropriately sort of bracket those choices when we teach to students about them. So we're going to look at the square root, and then from there we're going to have a conversation about exponents in general. After all, taking a square root is really finding an inverse for the x to the power 2 function. So exponents have something to do here. And the crown jewel of our discussion this week is going to be to take the exponential function, y equals e to the x, from the secondary curriculum, and figure out what that might look like as a complex function. What should it mean, for example, to take e and raise it to the i'th power? What should it mean to take any imaginary or complex number and raise it to a real or imaginary or complex power, right? What should that look like? And the exponential function there is the key to the kingdom. But unlike in the real variable case, the exponential function we study in the high school curriculum, the complex exponential function is not one-to-one. In fact, it is very badly not one-to-one. It's infinitely many to one. There are infinitely many different complex numbers that all have the same complex exponential output. And so being able to find an inverse for the complex exponential function, get a complex logarithm function, also involves that same process of choosing and potentially privileging one choice of inverse over the others. So that's the kind of conversation I hope that we'll get into this week. And what's so surprising is just the new rules that we thought were rules, but were only rules because we were working with real numbers. We're going to start to break some of those as well in our conversations this week. So this is going to be a little bit outside of our comfort zones, I think. So I'm going to try to take it slow, which means we'll have a few more videos for this set of questions than for the previous one. So stick with me. I promise the reward is worth it.